Hi guys, up to now what we have covered is, we have seen two types of transformers. One was a single phase transformer. There we studied about efficiency, voltage regulation, its performance, its equivalent circuit. And then in the last few lectures we covered three phase transformer. We saw various connections of three phase transformer, like we saw delta delta, which had a phase shift of 0 degree or 180 degree, and we saw star star, which also had a phase shift of 0 degree or 180 degree. Then we saw star delta, which had a phase shift of plus minus 30 or plus minus 150 degree, and we saw delta star, which also had a phase shift of plus minus 30 degree or plus minus 150 degree. And we saw open delta or VV connection, which had a capacity of 57.7% of delta delta connection. So this is what we covered in the three phase transformers, the various connection, their phasor diagrams and their phase shift. And we saw how to give namings to different three phase transformers. In this lecture what we'll be doing is, we'll be studying about parallel operation of transformers, that is, what is the load sharing by different transformers if they are connected in parallel. How does the current get divided among the transformers, and how does the power is shared between these transformers. That we'll see in this lecture. So parallel operation is nothing but there are more than one transformers, usually two transformers that are connected in parallel. Now why they are connected in parallel is because suppose only one transformer is there which develops a fault. Now usually power transformers are connected something like this. This is my generator, this will be my transformer, this will be my transmission line. Now what happens if this transformer develops a fault? No power will go from generator to the transmission line. So whatever the loads are connected here, all loads will get switched off. Okay, entire unit will be switched off, so all the loads will get switched off. But if we connect another transformer in parallel, then what will happen? If this develops a fault, we can disconnect this transformer and current can flow like this. That means we can still supply the load using the secondary or using the second transformer or using the other transformer. Okay, so that is why if there are two transformers in parallel, one goes out due to certain fault, other transformer can take the load and supply the different loads. That is why parallel operation becomes necessary. Other thing is that if both are operating under same time, if both are operating at the same time, then what will happen? The total current I will be sum of I1 and I2. That means now more current can be supplied. Okay, instead of I1 or I2, now we are supplying I1 plus I2. So more current can be supplied or more load can be supplied. That is, capacity of the entire system is increased. Now we can supply more load, or the transformer has the capacity to take more load. That is what is the benefit of the parallel operation. Okay. Other thing is that we know that power transformer operates at maximum efficiency when it is fully loaded. I told you power transformer is fully loaded during the entire 24 hours a day. So power transformer has maximum efficiency at full load, that is x is equal to 1. Now suppose due to certain problem load decreases at certain point. Then if two transformers are sharing the load, then what will happen? Both will be away from full load. Now none of the transformer will operate at full load. Suppose 0.7 I full load current is coming. This current will be divided amongst these two transformers. None of the transformer will operate at full load. That is, none of the transformer will be operating at maximum efficiency. Because for a power transformer, maximum efficiency occurs when it is under full load condition. So what to do is, we will switch off one transformer so that other transformer can operate at full load. That is at maximum efficiency. To operate other transformer at full load, we can switch off one of the transformers. Okay. Then the efficiency will be maximum or losses will be minimum. Okay. And the last thing is that standby transformer is not needed. Okay, since we are operating two transformers in parallel, what is a standby transformer? Standby transformer is a backup transformer in case main transformer fails. Okay, it is kept as a backup under the condition when the main transformer develops a fault and it has to be switched off. The backup transformer or the standby transformer will come into play and it will supply the load. So, the standby transformer is not needed if we are using the parallel operation, because already two transformers are there. Already reliability of the system is high. So, we do not need a backup transformer or a standby transformer. Now, there are certain conditions which must be satisfied for two transformers to operate in parallel. Now, whenever two devices are connected in parallel, the voltage across them is same. So, similar is the case with transformer. When they are connected in parallel, voltage will be same. So, we will say voltage rating of transformer must be same. Okay, both transformer must have the same voltage rating. Okay. Next is both must be connected with same polarity. Same polarity means, suppose I connect one transformer like this, other transformer also like this. Let us say this is dot and here this is dot, that is positive, positive. Now if we suppose apply KVL, I will go from here like this in a closed loop. Suppose this is voltage E1 plus minus, this is voltage E1 minus plus. As I told you, same voltage rating, so I am considering E1 and E1. So if we go from here to here, it will be minus E1, then it will be 0, then again minus E1. So total voltage will be minus 2E1. Now total voltage in the circuit is minus 2E1, and there will be some resistance of the windings. So there will be some current, that is minus 2E1 by R. There will be some current flowing in the circuit. This current is called as circulating current because it is circulating between the two transformers. This sort of current is always undesirable. Okay. Even if we are studying the parallel operation of transformers or generators or motors, any circulating current is undesirable because we want the loads to absorb the power. We do not want one load to deliver power to the other load. Similarly, we want transformers to transform the power, not transfer the power between them two. In this case, one transformer will be delivering power to the other transformer. But we do not want that. We want both the transformers to deliver the power to the load, but no power exchange should occur between the two transformers. For that, polarity must be same, that is this must be plus and this must be negative, due to which voltage will be 0. Okay. If voltage is 0, there is no current or there is no circulating current. That is how two transformers must be connected in parallel connection. Okay. Voltage rating must be same and polarity of voltage must also be same. Next is, for a three-phase transformer, phase sequence must be same. Okay. In a single phase transformer, we talk about polarity, but in a three-phase transformer, we talk about phase sequence. That is, if one has a phase sequence RYB, other must also have a phase sequence of RYB and not RBY. Next is, phase displacement between secondary must be 0. Okay. The thing is, we are saying the voltage must be same. In phasor terms, same voltage or same phasor means the same magnitude and the same phase. Okay. Even if magnitudes are same and phases are different, the difference will not be 0. Suppose E1 is this and E2 is this. Both have same magnitude but different phase. Then E1 minus E2 will be something like this. It will be non-zero. Okay. We do not want that. We want that whenever we are subtracting the two voltages between the two transformer, or the net voltage in the parallel operation should be 0 to avoid any circulating current. And for that to happen, the magnitude as well as phase of both the voltages must be same so that they can cancel out each other. If magnitude is same but phase is different, then also their difference will never be 0. So in case of three-phase transformer, we should connect those transformers in parallel which provide the same phase shift between primary and secondary. That is, star star and delta delta can be connected in parallel because both provide 0 degree or 180 degree phase shift. Or we can connect star delta and delta star transformer because both provide plus minus 30 or plus minus 150 degree phase shift. But we cannot connect star star and star delta in parallel because phase shift of both the transformers is different. So secondary voltage will never have the same phase, hence there will be circulating currents. Okay, that is why it must be kept in mind that the phase sequence as well as phase shift of both the transformers must be equal. These are the four necessary conditions that must be satisfied before connecting the two transformers in parallel. If you do not satisfy these conditions, then parallel operation will not be possible, or it will not work under desirable condition, or it will not work as required. Okay, requirements will not be met. Now these are necessary conditions. Okay, let us summarize those. First one was same voltage rating. Next one was same polarity to avoid any circulating current. Next, same phase sequence and same phase shift. These are four necessary conditions for parallel operation of the transformer. Now there are some desirable conditions also which ensure that the transformer operation is well and good. These are not the necessary condition, means even if they are not satisfied it is fine, but if they are satisfied the operation is better. Okay, for a better operation we must satisfy these conditions, but it is not that if these are not satisfied the parallel operation is impossible. Okay, these do not oppose or these do not stop the parallel operation, but they just can make it better. The first is the load sharing, that is SA by SB must be proportional to their rating. Okay, which means the transformer which has a higher rating must take more load as compared to the transformer with a lower rating. Okay, transformer with a higher rating must always share a higher amount of load. Why? Because the transformer which has higher rating is more equipped to take on higher load. Its winding will be thicker so that it can handle a larger amount of current. So it is just saying in general life, like whichever is more capable should do better. Okay, should achieve more. So A has a higher rating, so if then A load must be higher than the B load. So we must say that the desirable condition is load sharing must be proportional to the kVA rating. Next is X by R of A must be equal to X by R of B. Reactance to resistance ratio of both the transformers must be same. Why? Because phi A or the power factor angle is tan inverse XA by RA and phi B will be tan inverse XB by RB. Now if both X by R is same, phi A is equal to phi B, power factor angles are equal, or we can say power factors are also equal. So if you want to operate both the transformers at equal power factor, their X by R ratio must be same. Okay, that is a desirable condition but not a necessary condition. Is it fine? Now let us look at what is the equivalent circuit under parallel operation and how do they share the load. Now the secondary side will have a EMF, a resistance and a reactance. Similarly for the other transformer, resistance, reactance both are connected in parallel. Now there must be some load. Okay, load current, let us say I. This is RA, XA, RB, XB. So current in each of the transformer I am marking as IA and IB. These EMFs we can mark as EA and EB. Now, as per our necessary condition that voltage rating of both the transformers must be same, that is EA must be equal to EB. So I can replace these two sources by a single source, something like this. Let me call it as E, and both the transformer impedances like this. Okay, this is my load. I, then IA and IB. Now this is the case of simply current division. Since two impedances are connected in parallel, the current will be divided among the two impedances. So if I want to find IA, IA will be nothing but I into ZB over ZA plus ZB, and IB will be equal to I ZA over ZA plus ZB. Okay, this will be the currents in each of the transformer. Now if I want to find the power delivered by each of the transformers, suppose I want to find SA. SA would be V into IA conjugate, which will be V into I conjugate into ZB over ZA plus ZB conjugate. Okay, so VI conjugate will be load power into ZB by ZA plus ZB conjugate. Similarly, SB would be load power into ZA by ZA plus ZB whole conjugate. So this is my power of the transformer A and power of the transformer B. Okay, they are inversely proportional to their impedances. And remember, in this expression, whatever impedances we are using, these are impedances in ohm. ZA and ZB are in ohm. Okay, these can also be in per unit, but the base of those two values must be same. Okay, so either you can use both the impedances in ohm or you can use them in per unit, but remember their base must be same. Okay, how to change the base of any impedance? If we want to change the base, Z per unit new is equal to Z per unit old into V old by V new square into S new by S old. Okay, base values are, there are only two values, that is the voltage and the power. Okay, voltage rating and the kVA rating, these two are my base values. So if you want to change the base of any value, you must apply this expression. Okay, because most of the times what is given is the per unit value will be given to you, but that will be on the individual base. Like if one machine rating is 400 kVA and the impedance is given 0.2 pu. Other machine is 200 kVA and its impedance is given as 0.1 pu. Now you have two options, either change both to ohms or convert this 200 kVA to 400 kVA. How to do that? 0.1 into voltage rating, let us say we are keeping same, old and new voltages are same, into S new. The new power rating or the rating which you are going to is 400, which you are going from is 200, it is 0.2 pu. Okay, so we must transform the impedances on the same base, or we must convert both the impedances to absolute values. This you must always take care while solving a problem based on parallel operation. Again I am reminding, either both impedances must be in ohms, otherwise if they are in per unit they must be on the same base. And about this power, the thing is, suppose we are taking a lagging load, then we will say voltage is V angle 0, current is I angle minus phi, then S will be VI conjugate, that is V angle 0 into I angle phi. Conjugate is, angle is reversed, Vi angle phi. So for a lagging load, the power will have a positive angle. And for a leading load, V angle 0 and I angle phi. So S is equal to Vi conjugate, which is equal to V angle 0 into I angle minus phi. So Vi angle minus phi. So remember, for a leading load, the power will have a negative angle, and for a lagging load, the power will have a positive angle. This is just opposite to the current. For a leading current, we take a positive phase, and for a lagging current, we take a negative phase. But for a leading power, we'll take a negative phase, and for a lagging power, we'll take a positive phase. Okay, that is what will happen. Next, let us see, one of the desirable conditions was that the load sharing must be proportional to the kVA rating. So how can that be possible? What I am saying is, SA by SB should be equal to SA rated by SB rated. Now just now we saw that SA by SB would be equal to ZA by ZB. Okay, so sorry, it is inversely proportional to their impedances, so this will be ZB by ZA. Okay, let us say these both are in ohm. So what I can say is ZA into SA rated should be equal to ZB into SB rated. Now we know that the rated voltage on both the transformers will be same. So let us divide it by the rated voltage square. V rated square. V rated square. Now V square by S will give me Z base. So ZA by ZA base, it is equal to ZB by ZB base. So it is equal to ZA in PU will be ZB in PU. Okay, but this time both have their individual bases. Okay, earlier I was telling you, when we are applying the parallel operation, both must be on the same base or both must be in absolute values. But here, if you want to divide the power based on their kVA rating, or power must be proportional to their kVA rating, then their per unit impedances must be equal, where per unit impedance is defined on its individual base. Okay, so remember, for parallel operation, the values that you are substituting must be on the same base or both must be in ohms. But if you want the load sharing must be proportional to kVA rating, then their per unit impedances on their individual bases must be same. Okay, this is the condition for the power division proportional to kVA. Next is something called as Sumpner's test. Now when we were performing short circuit test or open circuit test, in open circuit test we were encountering core loss and copper loss was negligible. In short circuit test we were encountering copper loss and core loss was negligible. Now that means in both these tests we are encountering only one of the two losses but not both. Now due to losses in a transformer, the temperature of the transformer increases. So the temperature of the transformer will not increase by an amount which is equal to the working condition. What happens whenever the transformer is working? It will have both core as well as copper loss. So temperature increase will be higher. But when we are conducting open circuit or the short circuit test, we are encountering only one of the two losses. So temperature rise will be lesser. That is, the temperature rise that we will be measuring will be less as compared to what will be the temperature rise under working condition. So we are not estimating the temperature rise properly. That is the disadvantage of the open circuit and short circuit test. So we need some test in which core as well as copper losses will occur simultaneously so that we can estimate the temperature rise of the machine. That test is called as Sumpner's test. Here what we do is, there are two identical transformers. Okay, we need two identical transformers and their primary windings. One indicates primary and A and B are the two transformer. Okay, their primary windings are connected in parallel and their secondary winding are connected in series opposition. Series opposition means minus plus then plus minus. Their EMFs will be subtracted. Okay. So primaries are connected in parallel and secondaries in series opposition. Secondary winding is connected across a low voltage auxiliary supply which can be varied. Okay. So secondaries are connected in series opposition and their voltage can be varied by an auxiliary source. Now what are the steps to be performed in Sumpner's test? First of all, we will keep secondary open circuited and primary will be applied with rated voltage. Okay, so here we are conducting the open circuit test. But since there are two transformers, the no load current will be twice the no load current of each transformer and power measured by wattmeter will also be twice the no load losses due to two transformer. In the second test, our secondary will be applied with rated current. By varying the voltage, we will apply the rated current and primary will be short circuited. Okay. So here we are conducting short circuit test. So it will give current twice the full load current and wattmeter reading will be twice the full load copper loss. And in the third step, we will connect both the sources. None of the winding will be open circuited or short circuited. On both the windings, we will apply rated voltage and rated current. Okay. Here none of the winding will be open circuited or short circuited. And we will record the temperature rise. Okay. Temperature rise we will record, which will give us an idea of the how much cooling is required in such a machine, or whether the temperature rise under the working condition can be hazardous to the machine. Can it damage the windings or the core of the transformer? So that is the steps in the Sumpner's test. We first conduct open circuit test and then short circuit test. These two tests can help me finding the efficiency of the machine. And in the last test, we conduct or we connect both the sources simultaneously to estimate the temperature rise in the machine. Okay. So that is how Sumpner's test is conducted. So let us summarize what we learned in this lecture. We saw parallel operation, in which we saw necessary conditions. Necessary condition was voltage same, polarity same, then phase sequence same, and last same phase shift. Then we saw that SA was equal to SL into ZB by ZA plus ZB conjugate, and SB was SL into ZA by ZA plus ZB conjugate. Here ZA and ZB are in ohms or per unit, but per unit on the same base. And if we say SA is proportional to SA rated, that is load sharing is proportional to KVA rating, then ZA per unit must be equal to ZB per unit, where per unit values are on their individual basis. Okay. And last we saw Sumpner's test, which estimates the temperature rise in the machine by operating it at rated voltage and rated current, so that core and the copper losses are encountered simultaneously and not under separate conditions. Okay. So this is all about the parallel operation. In the next lecture, we will be dealing with the auto transformers.